Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to talk about the properties of limits and how they interact with the operations of other functions. So, in order to kind of reason our way through to how limits would work with other function operations, we first need to kind of set up our scenario. And here it is. We're going to suppose that we have some c that is a real number constant, and then two limits. We have f of x and g of x. And remember that as our part of our definition for limits, that both of these functions will exist on some open interval everywhere except possibly at a, and that as x approaches that a, both of these functions will approach some real number value. Now, it doesn't have to be the same real number value, but f of x will approach consistently a value, and g of x will approach consistently some other value. Okay? So, based on how, say, for example, function addition worked, how do you think limit addition will work? See if you can think through what you think it would look like. And I'll show you in 3, 2, 1. So, if that's what you guessed, good job. Your intuition was correct. And if not, don't worry about it. We will be proving this later, but for now, just think for a moment that the reason this works, or the reason we can kind of think through this, is because remember that the limit as x approaches a of f of x approaches a real number value, and the limit as x approaches a of g of x also approaches a real number value. Well, so does the limit as x approaches a of f of x plus g of x, because if this exists, it's also a real number value. Okay? So, you can kind of reason through how that kind of makes sense because these are approaching some value. And in order for us to be able to add two functions, they have to exist across each other's domains. So we're only really able to add these where they would exist simultaneously. And limits follow those same rules. We can't add the limit where they don't exist together. So if they aren't appearing in the same place, then they wouldn't be able to be added within that area. So, follows the same rules as all of our other functions do. Okay? So, based on this, you can probably reason out how it's going to look for subtraction, multiplication, and division. So, again, think it through, and I'll show you those rules in 3, 2, 1. So hopefully, based on the addition rule, you managed to get the subtraction rule, the multiplication rule, and the division rule. Now, one thing I want you to notice is that within the division rule, we did have to reinstate our whole worrying about dividing by zero. That's because we never actually stopped worrying about dividing by zero. It's just that in those specific situations where the division by zero caused us to be undefined, the limit allowed us to circumvent that, so we didn't worry about it. But you'll notice that over here, we weren't worrying about it because if x approaching a made us be undefined, well, we don't ever get to a, so yeah, we're not going to be undefined here. But here, this could potentially be zero, and zero may not be an undefined value specifically for this limit, but in this quotient, it would cause the quotient to be undefined, and we're not taking the limit of this quotient, we're taking the quotient of limits. So we have to worry that the limit is not equal to zero. Basically, what it is that in very specific circumstances, the limit is a guardrail that lets us circumvent the zero division, but it doesn't just magically make that disappear. It's always there. Now, really quickly, let's go ahead and just kind of explain how these rules are worded and what we call them. So the first rule is our uh, law of sums. And what this is we say that the limit of the sum of functions is equal to the sum of the limit of the functions. The second one is the law of differences. So the limit of the difference of functions is equal to the difference of the limit of the functions. The limit of the product of the functions is equal to the product of the limits of the functions. And then the limit of the quotient of the functions is equal to the quotient of the limits of the functions, given that the denominator is not equal to 0. And that would be our quotient law. Okay. Now, these 4 laws also bring about a couple of other laws that we're going to look at, and we're going to look at a few that are kind of obvious, but we do need to state them so that we can use them in the future. And here we have our additional laws. Up on the top, we have our product law, and this comes as a direct result of letting g of x equal f of x, and then just simply applying the product law in number of times. So as you can see, what we've done is we've said the function f of x to the n and then taken the limit, whereas here we've taken the limit of f of x and then raised it to the power of n. N is going to be in the set of whole numbers, and that's just ensuring that we're not actually taking a root instead, and that we're not doing something with, using rationals or just something with roots. Okay? And then from that power rule, we can kind of infer the root law, which works the same way. Now, it's not a direct inference. There's quite a bit of extra work you do when you're proving this one, but from a kind of intuitive logic, it would follow. Now, the one thing we have to make sure that we look at here is that the limit here of f of x or f of x itself would have to be greater than 0 whenever n is an even value. And then down here we have our obvious ones. And the reason I say they're obvious is because when you look at them, and you say them out loud, it's like, oh, well, yeah, of course. So, for example, our first one here, we're saying the limit as x approaches a of a constant. There, x has no effect on this constant because it's a constant. Constants are constant. They're not affected by the variable. So no matter what x goes to, c is always c. So therefore, no matter where x is, c is c. Okay? And then similarly here, we're taking the limit as x approaches a of x. So that means as x approaches a and gets infinitely close to a, the value of the thing we're taking the limit of will approach a value. It'll constantly be approaching a value. Oh wait, but x is constantly approaching a, so therefore the value that the thing we're taking the limit of is constantly approaching a. And then from that, we can then infer, oh, well, but if we take the power of that x, well, then yeah, we'll just again replace the x with a. And if we take the root, we'll again replace the x with a. And we'll follow the same rules down here as we did up here. So same n rule and same rule if n is even, where the a would be greater than 0. Okay. Now, we are going to look at 2 more properties for limits, but before we do that, I'm going to show you how we apply these rules in order to make it a little bit easier to decompose a complicated function when we take a limit. Okay, and so here's the problem we're going to try out. And what I'd like you to do is try to find this limit by hand. If you use the limit laws that we've just learned, it's actually not too difficult to do. So go ahead, pause the video, and give it a try. And I'm going to solve it really quickly and then walk you through it. 3, 2, 1. And there you go. So, starting at the top, let's look at the rules we used. So, here's our limit. We have the limit as x approaches -2 of this rational function, x cubed minus 2x squared minus 1 over 5 minus 3x. Now, really quickly, we just need to check to make sure that if we take the limit of the bottom, that it wouldn't be 0. And if we look at that and we look at the limit of 5 minus 3x as x approaches -2, it shouldn't be 0 because if we plug a -2 into there, well, when we get to the bottom, we see that it's 11. But we can do a quick look at that and see, yeah, that shouldn't be because 5 minus a whole number won't be 0. So we should be good. Okay, so we know that we're fine to go ahead and try it. Okay, so the first thing we do is we apply our quotient law and we take the limit of the numerator, the limit of the denominator. Okay, from there, in the top, we apply our, in this case, difference law. And in the bottom, we also apply our difference law. Now, this is where we get to our advantage, because if we didn't apply our difference law, we would have had to have factored the top to see if we would have gotten a 5 to the 3 or 5 minus 3x out of it. And maybe we would have, I don't know if we would have, and that would have been a little bit difficult. So I don't necessarily know that I would have wanted to try. So this way, it's just a little bit easier, right? It kind of got us around that, got us away from that. So we go ahead, we apply our limits there, and then after we do that, we could have started reducing things, but I like to apply the limit laws everywhere first and then go ahead and throw the limit into everything. So then from there, I had a couple of places where I needed to go ahead and apply the product law. Now, there actually was a limit law that I forgot to mention, and that was the constant law. But you'll notice that we can apply the product law, and it effectively becomes the constant law because of the constant law we had at the end. And all the constant law says is that instead of having to do the product law, and then take that limit, I just could have jumped the constant out from the beginning. But it's effectively the same thing because if I do the product law and then take the limit, it's the same effect. So effectively, you just proved the constant law from the product law here. So there you go. You got a free proof. Whoops. But so we apply the product law here, we apply the product law here, then I take the limits. Now when we take the limit here, we apply our power law that we had, that obvious one at the end, because we just have x as it approaches -2 going to x. Well, as x approaches -2, x would just become -2. -2 to the 3 is -8. -8. Same thing happens here, -2. -2 squared is 4. So 2 times 4 is 8. So we get -8. And then, of course, this is a constant, so it's just 1. So 8 minus, or -8 minus 8 minus 1 is -17. And then in the bottom, this is a constant. We apply our constant law. 5 minus constant, we apply our constant law, 3. And then here, this is just x. We apply our, it's basically substitution law. And that's a -2. 3 times -2 is -6, but that's subtraction, so it becomes positive. So we get 11. -17 over 11. Hopefully you got to the same place. Now, let's go and look at those last two properties we were going to talk about, and then I'll give you a couple more of these that you can try on your own. And of course, like usual, the answers will be at the end of the video. Okay, so here are our final two theorems. Now, the top one is a simple inequality theorem that tells us that if we have one function less than or equal to another function when x is near a, but not necessarily at a, and their limits exist, then the limit of the first one will be less than or equal to the limit of the second one. Okay, so basically this just means that if we don't know their values, we do know that their relationship will hold true when we take the limits. That can be helpful when we're doing proofs. It can be helpful when we're doing different types of integrals or different types of derivatives. Now, the second one is extremely important. And you know it's important because it has a name. We call it the squeeze theorem or the sandwich theorem because what we're doing is taking a function that is problematic to find the limit of, and we are squeezing it between two functions that we can find the limit of, as long as those other two functions fit a specific criteria. Okay? So the first thing that has to happen is the three functions have to be in this relationship when x is near a but not necessarily at a. And then the outer two functions have to have the same value when x approaches a. If that holds true, then what happens is they squeeze that middle function down to that same value. And what this lets us do is use two functions that we know their limit, or at least can find their limit, in order to find the limit of a third function that is just a little bit too problematic or where maybe we're having issues. Now, if you want to try out using the limit laws yourself, there's going to be some practice problems in just a moment, and the answers for those will be at the end of the video. So I hope that video about the laws of limits helped you out. And if you have any questions, remember you can always drop into the comments or join us on Discord. In the next video, we're going to talk about continuity.